Hey guys, this is Gavin from Sci-Fair Science NHS. I'm your webmaster for the 2020-2021 school year, and today I'll be giving the first in a series of online lectures aimed at both granting more opportunities for club members and entertaining and educating a more general audience. By the time this video comes out, there should be a new page on our website, you can find the link in the description, that goes into more detail about what those opportunities are going to be like. As you've probably guessed, today I'm going to talk to you guys about quantum computers. Now, a quantum computer is actually just like a normal computer, but unlike a normal computer with its normal physics, a quantum computer uses quantum physics. Now, chances are, if you're watching this, you probably don't know, one, how a normal computer works, and two, how quantum physics works. So we're going to start with the former. Computers, like your phone, use these things called bits. Now, what is a bit? Well, it's a thing. It's a piece of binary information, and it can hold a 1 or a 0. Often, it's thought of as a light bulb, right? So if you have a light bulb, it can either be, on, and that would be seen as a 1, or it can be off, and that would be seen as a 0. You've probably heard that computers can't think. Well, that's because a programmer has already defined all the information within them. For instance, let's use our bit again, right? We're going to assume that a programmer has put some kind of information into this bit that can let it read a question and then output an answer. So in this example, we're going to have a question that's input into the program, and then it's going to output either a 1 or a 0, standing for true or false. True and false are just normally the conventions for this. So let's say we have a red car. Now, because it can only answer with true or false, we can't ask the computer a more complicated question like, is the car red or green, or is the car blue and yellow? But what we can ask is if the car is red. So we ask the question, is the car red? It'll go through, it'll do its thing, it'll run through the program, it'll see if it's red, and if it is, it'll return true. Now, it's important to note that the computer doesn't know what's going on. The computer can't think for itself because all of its thoughts that it's having inside this box have already been designed by a person. We don't use computers to solve like quintessential human existence problems. We use them to run numbers really, really fast. Now, alternatively, if we asked the computer if this car was green, it would go through, it would think about it, it would say, that doesn't look green, and then it would return false. Okay, so what do you want to do if you have a multicolored car, for instance? Right? Well, admittedly, I lied a little bit when I said that computers can't take in more complicated questions like, is something red and blue? You can totally ask that question to a 1-bit system, but it's going to output nonsense because, it's not designed to take in 2 pieces of information. It's only designed to take in 1. So the way we would get around that is we would just add another bit, right? This one would be our red bit, this one would be our blue bit. If this one detects an R, it'll print out a 1, otherwise it'll print out a 0. Same thing with the other one. If this sees a blue or a B, it'll print out a 1. Otherwise, it'll print out a 0. Right? Not terribly complicated. So if we plug in an R and a G, a red and a green car, right? The red it sees an R, so it'll print out a 1. But the blue, it doesn't see a blue, so it'll print out a 0. Now, as you can imagine, there are 3 other states that this computer could be in. Right? Now, if you're paying attention, you might notice that the first computer that we built, we had 2 states that it could be in. It could be in a 1 or a 0, but now it can be in 4 different states. Now, so we went from 2 to 4. Well, if you know your powers of 2, the next step is 8, because if we had 3 bits, we could be in 8 different states, and the next is 16. So obviously, we're following some kind of rule where it's 2 to the power of something. Now, modern computers are, well, let's say a bit stronger than those examples I was giving. Yeah, my wonderful representation of what a computer looks like. A modern computer has about 2 to the 64 billion bits in it. Well, actually, it has 64 billion bits, and it can hold 2 to the 64 billion pieces of information. Right? That's a lot of information. I think the universe has something like 2 to the 80 particles in it. So this is 2 to the 64 billion. That's a lot of information that a single computer can hold, especially something that can fit in a cubic foot of space. Yeah, but the problem with these computers is that they can only do so well, right? You can add on a piece of information and it'll double in effectiveness. But what if you would need it to quadruple for whatever kind of problem you're working on? What if the problems got significantly harder than you could add on problems, right? Then calculating would be significantly more challenging. You'd have to double the amount of space that you need, essentially. In order to generate some problems that we have, you would need a classical computer bigger than the sun, which isn't really feasible, which is where we get into quantum mechanics. Now let me change the scheme here a bit. I'm going to change up to a darker scheme. I like that. Yeah. Okay, so let's get started. Now, the most important difference between a normal computer and a quantum computer is that whereas a normal computer uses normal bits, which can store 1 or 0, a quantum computer uses quantum bits, often abbreviated as qubits, which can store both a 1 and a 0 at the same time. Okay, so how does this idea work, right? Now, whereas before our example was a light bulb, right? We could have a light bulb that's off, which would be represented with a 0, or a light bulb that's on, which would be represented with a 1. Now we're going to use an electron. Now, you may know this or you may not, but electrons are always spinning in what's called the electric field. And it's all around them at all times. And so if an electron is spinning with the field, then it's in what we call a low energy state, which would be represented with a 0. And if it's spinning in the opposite direction of the field, then it's in a high energy state, which we would say is a 1. So these are also typically called spin up and spin down. Spin up for 1 and spin down for 0. And this will be really good for defining our binary system. So let's start with any old electron, E, right? Now, let's add a bunch of energy to it, right? Let's guarantee that it's in the spin up position because there's so much energy. Now, we could alternatively take away a bunch of energy and guarantee that it was spin down or in the 0 position. So what happens if we add a bunch of energy to it and guarantee that it's spin up, but then we take a little bit of energy away from it? Not enough to guarantee that it's in spin down, but definitely enough to guarantee that it's not in spin up. Well, we've put this electron into what we call a superposition of states, right? It stores a probability now that it is a 1 and a probability that it's a 0. It now stores twice as much information as it did before. Now, if we look at our classical bit again, right, this could either have a 1 or a 0. This new bit, this electron, can store both a 1 and a 0. That means it can store twice as much information. So, as you can imagine, if we made it smaller, right, we made our bit down to a quantum size, it's now smaller, and it holds twice as much information. That is a severe improvement on efficiency. But there's also some errors that occur when you have more complicated systems like this. Now, in order to understand what kind of errors I'm talking about, you're going to need to understand a little more about electrons themselves. Now, each one of these things can be represented with what's called a sine wave, right? And this is just basically a way to represent its behavior. It's going to have a thickness component, which is going to be how much is it vibrating, and then it's going to have a length, which is going to represent its how long it takes for it to vibrate. Every time it repeats, it starts another vibration. Right? So each one of these electrons has a completely unique sine wave, and when they interact, it's equivalent to adding these sine waves together. Right? So you might get something that looks like this, which admittedly looks like absolute chaos. So we really want to make sure that the right electrons are communicating with each other, right? If you think about it, if you have one electron, right, it's going to be right there, it's going to have a field like that, and it's going to communicate with every other electron in that field. Now, alternatively, if I have an electron over here, it's going to communicate with everything that it sees, right? It's interacting with this electron now, and this electron is interacting with this one. Now, say I have a third electron that I don't want to communicate with these two electrons. Well, I need a way to make sure that this electron barely touches these other two electrons' wave functions, right? Which is really hard when you only have so much space. So there are a number of things that we do to make sure that this doesn't happen. For this, let me use an example. Right, let's say you're at work and you broke something. Well, you would maybe, hypothetically speaking, discreetly look for the repair guy and try to avoid communicating with anyone else about this sensitive subject. Well, if you could find the repair guy right off the bat, that'd be great. You could communicate to him that maybe you broke something. He could communicate to you that maybe he could fix it, right? But otherwise, let's say that, maybe there's a lot of people in the room, right? It'd be really difficult to transmit that information discreetly, especially when everyone can see and hear you and possibly know that you broke something. So what a quantum physicist would do in this situation would, well, first of all, they would probably file a report because they're responsible. But what they would do secondarily, if that wasn't going to work, is they would not cease to exist. They would lower the temperature of the room to near absolute zero. They would make it really, 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 really cold. And what that would do was that would make everyone stop moving in the room. All these spheres that were intersecting before are now going to be shrunken such that all of these other people representing electrons aren't going to interfere with this communication that you need to happen discreetly. Now, this brings me to the next point, which is, where is any of this applicable? Well, one way this is applicable is with simulation, right? Modern computers can't simulate certain things, like atoms, or they can't properly simulate water, right? All of the things that we see in movies and TV, all of those simulations that they make, especially with it's called particle physics in computer graphics, but it's really not particle physics, is that it's all estimations of what they think particles would look like on the macro scale. But they can't actually simulate those particles interacting. They can just make guesses about what they look like. But with quantum computers, you can literally simulate those things. They've already made simulations of certain molecules with quantum computers. And what can you build with molecules? Oh yeah, everything else, including DNA, right? Including, viruses which hold DNA. That would be nice to fix. They can, simulate organelles in a cell. They can simulate cells themselves. That's a fun play on words. But, like, you can simulate all of these things with quantum computers. You can run thousands of simulations in a minute, and you're going to have so much more information than we could ever get with modern technology. Right, so that brings me to the ending topic is, well, how far away are these? How far until we can actually use quantum computers to their maximum potential? Let me draw a timeline real quick, right? And this is going to represent the lifespan of computers and computing, right? So in the 1800s, right, 1820s-ish, they came up with the first couple computers, and they honestly weren't that impressive. They could do a few cool party tricks, like the car thing, but they really weren't applicable in any other way. Then in the 1940s, we finally found some pretty, I guess useful uses for them, that I'm not necessarily going to get into. And then, in the 80s and 90s, people started using them regularly. We started selling these as commercial products. And now everyone holds what they would have called back then a supercomputer in their back pocket, or in their front pocket, if they're aware that people can steal phones from your back pocket. But now, where are supercomputers? When are we going to be able to have access to them? Well, there's a long answer and a short answer. The short answer is, well, we won't. Quantum computers aren't really things that you can scale down in the same way that a classical computer can be scaled down. If you think about it, the actual computer part is an electron, which you can't really get much smaller than that, being honest. Now, if you want to scale down the machinery itself, right, like the refrigerator, well, you can do that, but you can only do that so far before it becomes ineffective, right? There's only so much heat that you can remove from a system. So that comes down to how are supercomputers going to be utilized? Well, hopefully in a server farm, right? Already they have, well, IBM has. IBM is always ahead of these things, honestly. They have an open source quantum computer on the internet. It's out there. You can go and sign up for it, you can go and sign up to use it. And you can learn how the beginnings of programming on a quantum computer. Now, that being said, hopefully in 20 to 30 years, maybe 40 if, we're unlucky, we're going to have these massive quantum server farms that are going to be open source, that you're going to be able to access from your home. Kind of like how you pay for your internet bill. You might pay for your, quantum computing bill. Now, this isn't to say that quantum computers are going to replace modern technology. To be honest, they just can't. They don't have the ability to. You can't have a home quantum computer. It's not feasible. But what you can have is a classical computer at your house. And you can access a quantum computer on one of these server farms from that home computer. So in 20 to 30 years, you're going to have, plenty of universities and whatnot using this amazing technology to fix so many problems that we have in today's world. Now, don't get me wrong, they're not a, end all for all of, the world's problems, but they're definitely a good step in the right direction. Thanks for watching.